Okay, so let's start our training script. So I've created a project here just called Training FT Demo. I've already created a virtual environment using Python 3.12. So if I check by using Python 3 dash dash version, I can see that I'm on Python 3.12.3. And I'm using Windows Subsystem for Linux here, but you could use any recent version of Linux to do this. I would stress that this is a PC only thing. I don't know how to train on a Mac. I don't think it's very easy. So actually, let me correct myself. PyTorch does have support for Mac training, I believe, but I don't know what the state of that is. And we're not going to be really using PyTorch directly to train. We're not even using like pure transformers. We're going to be using a library called Unsloth. So if you need a GPU, again, you can go to Google Colab. So Colab here is very useful. You can have a free T4 GPU. You can also rent some cloud resources, but there are a few good deals out there for laptops or computers that do have older generation GPUs. In fact, I kind of encourage that it is slightly older because there will be more support and it's easier to just install dependencies and all that stuff. So, for example, take like the GeForce RTX 5000 series, the Blackwell chips, for instance. Support for that when it comes to like fine tuning and training, it's like hit or miss depending on what you want to do. So actually, if you can find like a secondhand laptop, for example, or a refurbished one here for quite cheap, with from last generation, it is actually not that bad. You can train with it. This one has eight gigs of VRAM, but that's going to be okay because the model that we're going to be training is going to be pretty small, and it's just fine tuning with LoRa anyway, so it's not going to use that much VRAM. And so the library that, let me just see the video RAM. It doesn't say the video RAM here, but I'm pretty sure the RTX 4060 is 8 gig VRAM because on Newegg it says it's 8 gig too. But anyway, there are a lot of fine tuning libraries out there. One of them is going to be Unsloth, and Unsloth is a library that makes fine tuning a lot easier. But for today, we are going to just try and fine tune with normal transformers. So we're not going to be using Unsloth. We're going to just be using transformers to fine tune. So we're not dependent on this library, but we are going to be using the Unsloth Gemma 3 270M model because it's not gated from Hugging Face. So yeah, let's get started. So first things first, you want to import the data set that you've created. So here's mine. I only have 34 examples. So for today, we're just going to try and see if we get anything different from our fine tuning. The next thing is we need to install some dependencies. And the main dependencies that we need to install are transformers, and I think that's it. So let's install transformers and then see if we can just go directly or if we also need PyTorch. But I think PyTorch is probably installed with transformers in this case. You know what? Let's actually just install PyTorch too because I think it's good to know how to do that. So in this case here, I have A4000 GPU here, and I know it's working on Whistle because I see it on the Linux side of things by doing NVIDIA SMI. So if I were to go to search for PyTorch to get PyTorch, I'll go to pytorch.org, and there's a getting started button here, and I'm going to deny non-essential cookies, and I'm going to scroll down to here. Now, at this point, as of today, PyTorch 2.9 has been released, and I want to download the latest release. And so even though I am on Whistle, Linux is going to be the OS that I choose here. I'm going to use pip Python, and I am going to choose, let's see, what CUDA version am I running here? CUDA version 13. So using NVIDIA SMI, I can find out what my CUDA version is. So I'll choose CUDA 13. I'll just copy this command here, and I'll go back to VS Code, and then I can just paste that in here. And since I'm already in my virtual environment, this command will install Torch into my virtual environment. So I'll just hit enter for it to install those libraries. And then after that, I can just install transformers or any other thing that might require PyTorch in the future. Okay, great. So PyTorch installed successfully. So now we need to install transformers. So transformers is a library from Hugging Face to allow us to do stuff with transformer models. But we also need TRL too. And so we'll install both of them. TRL is actually the library that does the training using transformers. So let's do both of that. So we'll do pip install transformers, and let's take version 4.57. I think 0.1 is the latest one, and then we'll install TRL at version 0.23.1. And then it'll install both of these packages, and it should be fairly quick. They're not that big of packages, especially since we already have Torch installed. It doesn't have to go through all that like process in trying to install CUDA and all these other things that are required. So while we're waiting for that, we do need a git ignore, so maybe I can just install a git ignore here. So npx git ignore python, and that should create a git ignore for Python here. And we need to also bring in our prompt so that we can use as a system prompt for our data set. And so if you remember here, our system prompt was this one from the very beginning, and we had used this on I think Qwen 1.7b, and it worked quite well. And I think we used it on Gemma 270M, and it didn't work well. So just to I guess remind ourselves, let's run that again with Gemma and see what we get. So if I loaded all this up here, let's see, I don't need to offload to GPU. I'll just remember the settings here. Reason why is because I don't want to forget that I had it loaded, especially when I start training. It's just going to take up RAM, and this model is small enough anyway. So I'll click on that wrench to paste the system prompt here. So copying that, so let's go to LM Studio and paste that system prompt, and then let's just give Gemma this prompt here to see what it produces, to remind ourselves how it attempts to decompose a task. So at this point, it shouldn't even make sense. Yeah, so it didn't even really adhere to this this prompt. So maybe if we decrease the temperature by a lot, let's just say 0.05, and have it regenerate. Okay, so yeah, it's not very good at understanding that. And maybe because Gemma doesn't really have a system prompt. So let's see what we can do. Let's create a prompt.py. That's going to hold our system prompt. So in this case, we can simply define a def get system prompt function, and it will just return the system prompt. Okay, so we'll paste the system prompt in. Oops, that was our user prompt. Let's paste the system prompt in this one. Okay, so here we go. So this is the same prompt that we've had to tell it to be a GUI planner, and we gave an example here, so it should know. So we just return that, and we'll be using that as we're writing our training script. The next thing we need is the training script. So this is going to be the script that we're going to run to train our model, to fine-tune the model. And I'm going to need a lot of space here. So, okay. So first thing is we need to define the base model. So that's just going to be an ID so that we can pull it from Hugging Face. In this case, we want to take it from the unsloth repo. So we'll say unsloth/gemma3 270 MIT, and that's going to be the model that we want. And we are going to import auto tokenizer and auto model for causal LM from transformers. So let's just import those two things, and we'll need that to load the tokenizer and the model, okay, from disk after we download Gemma 3 270 MIT. Okay, so auto model for causal LM. I think that's what it was. Okay. Now, first thing is we want to load that model. So model equals to auto model for causal LM dot from pre-trained. Okay, and this takes in model name and path. So in this case, we'll just pass in our base model, and then our D type is going to be float 16. So we can import torch here, and we can just access torch's D type of float 16. And then device map, we can just say that's auto. Okay, so now we've imported the model, and now we need the tokenizer. So let's import the tokenizer. So again, the model will have both like the model files, like the weights, and then you need the tokenizer to be able to kind of give input to the model. So in this case, pre-trained auto tokenizer for pre-trained takes in a single argument. That's mandatory. Is going to be the model path again. So both of these two are going to be taking in unsloth/gemma3 270 MIT. And then next, what we want to do is we want to do LoRa fine-tuning, which is basically going to only train a subset of the parameters of the model, so that we don't use a lot of resources. And it's also just kind of think of it as like just really truly fine-tuning the model, where we only create like a matrix that will have a certain specific rank, and we have also the model weights. And what we do is we want to train the smaller matrix, and when we're done, we'll apply the smaller matrix on top of all the weights on the model itself. So in order to do that, we need another library called PEFT. So we'll just pip install PEFT, and that's also quick too. So now that we have the PEFT library, we can just import LoRa config and get PEFT model. So from PEFT, import LoRa config, get PEFT model. So get PEFT model is going to prepare the model to be LoRa fine-tuned. It's going to wrap a lot of the LoRa stuff around it, and allows you to kind of train using LoRa fine tuning. So we're going to define a LoRa config first so that we can begin our wrapping. So LoRa config is going to be LoRa config, and that's an instance of the LoRa config class. For our hyperparameters for LoRa, we'll just start out with rank of 32. LoRa alpha is also going to be a 1-to-1 ratio, so it's going to be 32. There's going to be no LoRa dropout. And then our target modules, and I'll come back to this later. Bias will be none. And then our task type is going to be causal LM. Okay. So our target modules is just basically the like the I guess the matrices that we want to train, like the tensors, the weights. And so we're going to train pretty much all the linear layers of the language model. So in this case, we'll train like the query key value and out projection layers, and also the MLP layers, which is going to be gate proj, up proj, and down proj. So it's pretty much the whole thing. So we'll define that here with Q proj. That's one of them. That's one type. And then we are going to also fine tune K proj, and we're going to fine tune V proj, O proj, and then gate proj, up proj, and then down proj. So we're kind of going pretty hard, right? Normally, I think we only want to do Q and V, but we're going to do all of them. So it's also a small model too, so it's not, I don't know. Anyway, so now we want to wrap our model with the LoRa stuff. So we'll just reassign model to be get PEFT model with the original model passed in and the LoRa config. Okay. Next, we need to get our data sets. So let's write in pseudocode here. So oops, get open our JSON-L data set. Okay, and what we want to do is we want to convert each entry into a data set entry fit for conversation, and I'll show you what that really means. Okay, so actually, let's do it right now. So if a good example I want to show is an Unsloth notebook here, because they have really good examples. So going to the Unsloth website, you can see some of these notebooks here that relate to various models. In this case, there is a 270M notebook here, so the same type of model that we are going to fine tune, and they also use Colab too, so it's also free. So in this case, here's where you actually set up all your libraries. In this case, it's using Unsloth, and then you'll import the model and tokenizer in one go, and you can specify various quantizations for training, and then you'll define the LoRa hyperparameters, along with just wrapping that with the configuration to get a LoRa ready, model. Okay, so now in this case, there's a chat template that they use. In this case, for us, I don't think it's going to be that important. I think we already have a tokenizer chat template helper here, so we're not really dependent on wanting to know what they do to implement this. It's already probably provided for us in our TRL or transformers library. So here it is. So this is called chat ML, and this is the format that we had to convert every example into. So yeah, our JSON-L file is going to be converted into an object that has conversations as a key, so it's a dict, right? And it's going to be an array of these message type things, which is similar to what you would see with an OpenAI API. So that's what we had to do. We had to like write these converter functions to kind of transform our data set. And then once we do that, we have a formatting function for collation. And this is actually just going to batch our data set examples correctly with the chat template. And then yeah, and then we have our training parameters. So let's take this step by step. So the first thing we want to do is we have a JSON-L file. And what we want is we want to import this into a Python list. So in that case, we need another library, and that is called JSON lines. So we can pip install JSON lines, and that'll allow us to just read in a JSON L file into a Python list. And let's do that right now. So let's like import JSON lines, and we can simply do something like okay, so I was on the verge of using it incorrectly, but anyway, it's with JSON lines dot open, and we want to give the path to the file. In this case, it's within our dataset directory, and it's going to be called plans v1.jsonl, and we want to read the file as J. In this case, we'll import it as datasets, and then J dot, I think, read all. Read? I think this is read. Yeah, I think this is read. And we can just cast that as a list, and I think magic happens. So let's print what that has, and then we'll be more confident about what we're doing. So in this case, we can just start quickly testing now. It's going to take a bit of time to do that initial test because we have to load the model, and then we can actually load our data set. So yeah, okay, so Python train.py, and that should activate model download. Yeah, so it's going to download the model. In this case, it's 536 megabytes, and it's 270 million parameters. So that makes sense. 270 times 2, because there's going to be 2 bytes per parameter. That totally makes sense. Okay, so in this case, we only read the first. I don't know what this is. Okay, so it's actually not dot read. It's just casting it as a list directly. That's kind of weird, but okay, sure. So I ended up printing all the examples here, but a better way to do it is just to print out the first one, and that can give you a sense of whether or not you're doing things correctly. So anyway, we do have our data set loaded in as Python list right now, and each entry in the Python list is going to be a dictionary. So what we want here is our user message is going to be the goal, and then our I guess our ground truth is going to be our assistant response. There we go. Our assistant response is going to be this instruction subgoals here. It's currently in an array, but we want to concatenate all this into like a bulleted list like this, for example. Okay. So yeah, and then after that, we want to also import the system prompt here. So we have our data set now, and now we want to write our converter. So in this case, it's just a simple function, just like how Unsloth did it up here somewhere. Where is it? I think I missed it. This one right here. So it's pretty easy. So let's just write our own quickly. So in this case, let's call it def convert to chat ML with an example as our argument, and then we are going to take that example, and we're going to create a user message, and it's going to be example with goal. Okay, and then our assistant message is going to be example instruction subgoals. Now in this case, This is going to be just a flat string that looks like a JSON array. So we kind of want to load that as a JSON and then go through it and create a string instead. So we'll import JSON and then we'll, deserialize this into a real JSON array. So JSON.loads, loading that string into an assistant message, and we probably say assistant message list. And assistant message is going to be an empty string, and then we can just iterate for a in assistant message list. We can concatenate, okay, assistant message with a hyphen, and then also the current element in there, and then finish that off with a new line. Okay, and so that's going to be in our conversation that we're building up. And then we also need a system message. So system message is going to be get, what do we call it? Get system prompt. So get system prompt, and we're going to import that up here. So from dot prompt import get system prompt. Okay. So now we have our system message, our user message, and our assistant message, and we want to create that conversations object. So in this case, it's going to be an array. Okay, it's just like how Unsloth did it here. It's going to be an array of all these three things, and we're going to store it as a dictionary where conversations point to this array. So we're going to try and mimic that. So let's just create the messages, and then in here we're going to have, let me just get rid of this. Okay, there we go. Okay, so we're going to have a role of system, and I think that's a valid one here, right here, role system. And then we're going to have content, and then system message. Then we're going to have a role of user, and then content is going to be user message, and we're going to have role of assistant, and content is going to be the assistant message. Now we're going to return that as a dictionary where we have a conversations key pointing to the messages. So that's going to be how we're going to build every single example that's going to go into our model for training. And so the goal here is to have the model be able to match against, like, its predictions against this part here, right? So that is what we're going to try and get our model to predict. So let's see if we can actually convert one of these examples and see what happens. So let's just print converts to chat.ml dataset 0 and see what we get after applying our conversion function. And so if we run that, we should be getting an object. Attempted relative import with no known parent package. Oh, I see. Okay. Can we just... Sorry, I'm very lazy. I'm just going to not import it. I'm just going to define it up here. There you go. Just one nice training script. Okay. Great. So here we are. We have our one single transform example. And so if you look at the assistant message here, where is it? Somewhere. Role system. user content, and then right here. Okay, so role assistant. So you start out with 1, 2, 3, 4. So notice the new lines here. So we're adding new lines after every one of these entries. Okay, so now that we have that, the next step is to write iteration so that we can transform all of the dataset examples into this chat ML thing here. I think what we can, I'm not sure, but I think Transformers expects a dataset to be like literally a dataset's object. So maybe from datasets, import dataset. Okay, yeah, there we go. So we can first transform our dataset into real Transformers dataset object, and we can do that with from I think it's from list. Yeah, from list, passing in our list. And so now our data set is like a legit like data set object, not just like a normal Python list. So just to verify, we can also just print out the first entry here, and I think now it's going to behave differently. So if I hit save and then try it again, this is going to be different, or it's going to make it different. It's going to make a legit data set object in this case. Oh, yeah. Okay, so oops, we haven't applied anything yet, but yes, it's still good, right? So that's the original. That's what we have originally. So now what we want to do is we want to apply the conversion function by mapping through everything with this function as like a callback function. So every entry is going to be converted. So as we iterate through, we're going to pass each entry into the convert chat ML function, and then now when we do dataset 0, we should have our transform version. Cool. So now everything's been transformed again. Next step is we need to write our formatting function for what the trainer is actually going to be receiving. So def formatting func prompts, formatting prompts func. That's going to be our conversion from taking all of this and converting it into a proper format that Gemma actually expects. So we're going to apply the chat template on this. So in this case here, it could be that it's coming in a batch. So we do need to consider that. And there's something about Unsloth that is, there's like a caveat in terms of we have to remove the beginning of sequence token in the beginning. But what we're trying to do is we're really just applying a chat template, and then we're going to remove one token from this chat template to make it so that everything works well. So in this case, for a batch of examples, right? Taking a batch of examples, we can get the conversations associated with that batch of examples. In this case, the key was conversations. Okay. And now we want to get the text, which is going to be for every one of these conversations, we're going to apply the chat template using our tokenizer, the one that we had initialized way back up here. So that provides you with the apply chat template method, and we can pass in the conversation item. We're going to say tokenize is going to be false. We don't want to turn our chat format to be numbers yet, like tokens yet. And we are not going to add a generation prompt because we're not inferencing. We already have the assistant message provided. And then once we had the chat template, we can remove prefix of BOS. So this is the beginning of sequence token. It's unnecessary apparently. And we want to do this for every convo in Converse on Convos. Okay. Now, once we have the text, we want to return another dictionary with that specific text. So a list of text from this. So that's going to be the data set that the trainer sees. And so we had to transform again. So data set equals to dataset.map, formatting prompts func with batched equals true. So now it's going to just take a group of examples at a time and transform it. Okay, so let's see if that works. We should not be getting any errors. Okay, so yeah, notice how it processed all the 34 examples here from here. Okay, now finally, let's write our training loop. So we need to create some training arguments. So now we had to tap into TRL and import SFT config and SFT trainer. So we go back up here. Let's import from TRL SFT config and SFT trainer. So these are the two things that we will need to configure our trainer. And so scrolling back down, we have our LoRa model here already. So we want to just use that. So let's create our training arguments first. SFT config. So that's just an object. It's just a key value pair of stuff. So our dataset text field is going to be text here. So we're telling it, okay, given this data set, this batch here, like access this field to get the data that you want per device train batch size. For now, let's leave it as 1. So we want to process 1 example per batch. You can increase this as needed. Gradient accumulation steps. We can say, okay, let's just keep that as 1. So we'll process again 1 example at a time. Warm-up ratio is going to be the percentage of examples that you want to warm up with. Usually we do anywhere from like 3 to 5%, at least for me. And then the number of epochs you want to train for. And in this case here, we don't have much data. And so 1 epoch is definitely not going to be enough. We have to go through a few epochs. And for this amount of data, it's going to be closer to 5 more than anything. We're going to have to adjust this as we test. Our learning rate is going to be quite high relatively because it's a small model and we don't have that much data. So let's just start out with 1e to the -4. Let's log every single time. And then our optimizer is going to be Atom W 8-bit. And then weight decay. Oops. Weight decay is going to be 0.01. Our LR scheduler type. Let's just do cosine. So it's going to have like a very slow drop off. And let's have a seed that's reproducible so we can reproduce our results. Let's just set it to 42. It could be any number. Output directory, so where we're going to store our checkpoints and our model. And then report to, which is none. We're not going to report to any platform like TensorBoard or anything like that. So that's the training arguments that we're going to be using. Most probably what you're going to care about is just the learning rate and the number of epochs that you're going to be training for, and also maybe the batch size. But we have 16 gigabytes of VRAM here, and it's a small model, so this can actually be increased for sure. And in fact, it might be like you want to increase this for like a smoother like training run. Otherwise, like the weights are just going to bounce up and down. It's hard to tell if progress is being made. But I feel like this thing is so untrained that I think you'll just see it decrease anyway. Anyway, so now we just initialize our trainer with SFT trainer. We'll pass in the model. We'll pass in the training data set. We don't have a validation data set yet because I want to be able to use all the data that we have. Let's expand on it in the future and add an eval data set. but that's down the line. Arguments is going to be the training args that we have. Okay. Now, at this point, we're not doing anything yet, right? So like we haven't executed training, we're just setting up the training. What we really want to do is we want to call trainer.train to actually start the whole training process. So you just need this line here to just start running every single thing. And why is this not being colored? I think I'm okay though. Okay, so trainer.train is what you want. Okay, so now that we have all that, let's just see what happens. Let's see if we can actually start training. So I'm going to clear, and I'm going to just start training and see what happens. Okay, so hopefully it detects my GPU, and then we actually see something. Okay, so we're processing our examples, and now we need to have bits and bytes installed, so that's another library, pip install bits and bytes. Okay, and then let's see what happens now. So in this case, yeah, it's a small model, but it's still pretty tough on my computer. So okay, great. So now you see that since we're doing 5 epics, we have 34 with a batch of 1. It's basically how many iterations are we doing? Let's see. 34 times 5, that's about 170. So yeah, 34 examples 5 times, and then you can see that we have our loss right here. That is slowly actually going down, right? Or it's going down slowly, and yeah, it started out pretty high in the beginning with 3, and now it's learning quite well. And in fact, this shows that it's not a hard problem at all. So yeah, let's see. So really here, nothing's really going to happen because we don't save the model. But I just want to show you like there is GPU activity here. We're going to have to save it separately. So I'm going to quit. Okay, I'm going to quit, and I'm going to show you how you actually save the model. To save a merged LoRa model after training with the TR library, you first merge the LoRa adapters into the base model using the PEFT library. Okay, so our model should have that. So merge the LoRa weights, okay, then save the merged model using the save pre-train method, and then save the tokenizer. So tokenizer and model has to be saved together. So in this case, here's the example code. So it's going to be the model merge and unload. So merge the LoRa adapters into the model, and then we save the merged model to our output directory, and then we'll save the tokenizer with it, and you'll see that both are going to go in the same directory, and you'll have all the files there. And then after that, we actually had to convert it into a specific format so that we can try using this in LM Studio, and that's called a gguf file. So now we need to install llama.cpp too. So here, so when we're done, right, training, we can say model dot, what was it again? Merge and unload. Then what we want to do is we want to save pre-trained for both the model and the tokenizer. Okay, so let's save it to the outputs directory, which we already have here. So model dot save pre-trained outputs tokenizer dot save pre-trained outputs. Okay, merged model. Okay, I failed myself, not Google. So let's do that again. And this time, since this did not come out clean, I'm going to make a directory that looks like this. So this way, we actually have something more organized. Okay. Model. Okay, so that's much better. So let's finish training again, and this time, we have the right files. So we have the safe tensors file, which is expected to be about 500 some odd megabytes. So we're going to use this to perform some inference. And so we could inference here using transformers again. So what we can do is we can actually write some inference code and then inference through there with a generation prompt. And let's actually do that before we actually do anything else. And so let's create an inference.py, and let's just copy and paste a bunch of stuff. In this case, we'll just need the transformers code, and we'll probably also need, let's see here, maybe the torch. Yeah, maybe torch. Okay. Oops. Okay. So we have these two, and then we're just going to copy maybe these two lines here to just load up the model. In fact, let's do this. Let's get all three of these, and then let's also copy the system prompt. Okay. Now our base model here is actually going to be our new model that we have fine-tuned. So it's going to be in this path here. We can just copy relative path, and we're going to replace that with a path to our model. In this case, actually, absolute path also is good too, because then we have things that always confuse. So this will for sure work in this case for transformers. Sanity check by inference, starting our inference script. And let's see if it can actually try and load the model. So it always makes me nervous because it's just slow to load. But yeah, we get nothing, which is good, which is really, really good, because if we print the model here, we should be able to print the model architecture. And so like the next step is really just to perform some sort of inference on it. So in this case, it has loaded correctly as a Gemma 3 model. So all that's great. Now, if we remember going down here, we did have this chat ML thing here, right? So let's do this. Let's create this. Let's just by hand create one of these and then apply it to the chat template. And instead we'll also add the generation prompt. Okay. And then we can apply inference on the model. Okay. So a good source, again, let's go back to our notebook here for Unsloth. What they do afterwards is after training, they will apply the text here. So they create, again, all these messages, and then with the system message and only the user message, this time no assistant message, they'll apply chat template and remove prefix of the beginning of sequence token, but adding the generation prompt to trigger the model to start to generate the assistant response. In this case, we just call model.generate with the tokenizer passed through, tokenizing the text, returning tensors as PyTorch, and then moving that to our CUDA GPU. We could also control all the other inference parameters here. And I think we don't need the text streamer, but what that does is it just starts to like kind of stream text as if it was like kind of like ChatGPT, right? Oh, here he has, or he, Daniel and his crew, they also have code to save the model. But yeah, let's try to mimic all this. In this case, I'm just going to copy and paste this in copy selection. And then going back to the inference script, I can just paste. And then the system message here is going to be get system prompt. And let's just give a variation of our user prompt here. So let's, instead of 24, let's make the font smaller. So let's make the font size smaller to 12, for instance. And then we're going to get this tokenized text, and let's just see what that actually looks like. So we'll print text, and then we will run inference code again. Oh, what happened? Let's see here. Tokenizer, apply chat template. Did we not load the tokenizer correctly? Why is this here? Okay, so apparently it was a bad copy and paste. I didn't return the prompt. I only copied partially the function here, so maybe that's the reason why. So there was like a none type. Thank you. You caught it, Klein. Let's see. Okay, great. Cool. So we do have something coming out from the model. So here is going to be our system prompt. So it prints everything as like literal. And then we have our user prompt concatenated with the system prompt, because that's how Gemma works. And then we add the generation prompt. So basically start a term model to start triggering the model to generate. So now we need to write the generate code. And so again, I'm lazy. Let's just copy and paste. You know what? Let's just add the text streamer. Yeah, let's just do that. Okay. Maybe it worked. Maybe it might not work. So, okay. So text streamer here. Let's do max new tokens. Let's just give it 1024 instead. And then temperature, we want to stay pretty low. So I'll do 0.3. And everything else can stay the same. So the text here is going to be from this tokenized text, or not tokenized, but chat formatted text already. And it's going to tokenize the text here and move all those tokens to the GPU to compute. And then I think the streamer will just run in this case. So yeah, it should just start streaming. So let's see what happens. Oh, I didn't even save. Oh, and skip prompt is cool because I guess that's it's to output the response instead. And what is going on here? Assert. Okay. Model.generate. So just don't blindly copy and paste, because we do still need to put our model in eval mode, and then just set with torch nograd. Then we'll be able to generate output. Also, one thing is just make sure that when you load the model, just don't provide a D type. Just let it figure out on its own. Float 16, in this case, I don't think that it was trained specifically on that. Oh, it was, but I don't know, something was wrong. So by inference, I should get text to start generating, and I think in this case my GPU is working. Okay, and you'll see that you do get a plan back. So ensure that the document editing view is visible. Navigate to the toolbar, locate the font size dropdown, click on the font size dropdown, scroll to find 12, and then click on 12. So this is exactly kind of like what our training data showed. In this case, we can even say change to use heading 3. and we should be also getting like something different. Like, it's not always about font size. In this case, like Gemma has learned the pattern in doing things like changing headings, doing changing font sizes, and possibly even more, since even though that's like the only two things that we stressed on in our data set. So yeah, this is just like a basic like training script that we're going to just develop, and then hopefully have a validation set as we have more data. Yeah, next one will probably convert this model here with safe tensors into like a GGUS so that we can interact with it in LM Studio. And then I think that's good for today. Thanks.